Let's move on to the next speaker. He is deep learning researcher at the Intelligent Systems Unit at RISE. The title of the presentation is Artificial Intelligence in Industrial Practice, Opportunities and Limitations in General. I'm happy to give the stage to Erik Ylipää.
So thank you very much, and I'm very happy to be here. So my name is Erik Ylipää, and I'm a researcher at RISE. I work with deep learning, in particular for applied projects like time series forecasting, computer vision, music modeling, natural language processing, and lately on molecular property prediction, or chemistry and AI in general. So today I'm going to take a step back and talk a bit about AI from an kind of overview and issues with AI. So I think the keynote speech was an excellent introduction to what I will talk about. It talked a lot about the practical issues I will touch on. So first of all, one of the motivations for what I want to talk about today is kind of the cycles of AI progress. So the history of AI have seen these, let's say, bust and boom, or boom and bust cycles, where we've seen some progress, and in particular we've seen some tremendous extrapolations of the current trend in AI. And eventually the actual progress and this extrapolation starts to halt. What we've seen time and time again is that when this happens, like the hype kind of falls flat, a lot of the funding starts to dry up. And as an AI researcher with a deep belief in that the technologies we're developing are really useful, it is sad to see these kind of plateaus where progress really halts, mostly because this overinflated belief in what we can do. So before I continue to talk about these issues, let's just talk a bit more about this concept of AI. So a common definition, and the one I use, is that AI is a study of machines which can solve problems that humans use solve by using their intelligence. So that kind of skirts around this issue of trying to define what intelligence is, but at least we can think of any kind of problem solving which we humans typically solve by intelligence is something, when we use a machine, is part of AI. Now this is also quite broad definition, because a lot of the classical planning techniques and optimization techniques that we routinely use today to solve these kind of problems, they can also be considered as part of AI with this definition. So one thing to point out, it's not about machines which learn and think like people. So some part of AI research is, but that's a very small part of it. When we talk about AI these days, it's often some kind of machine learning we're actually talking about. And this is my focus today. So with machine learning, what we think about in that case is kind of it's a software, it's a piece of, it's a program which takes some input and produces some output. Or we can also think of it, we have some state in the beginning, and we run an algorithm which then at the end will have transformed that state to a new state. So traditionally we solve this kind of problems using rule-based methods or classical computer programs. So that's a rule-based algorithm. But the idea with a learning algorithm or machine learning is that we can actually, instead of having to specify the rules, we can kind of find the rules by numerical optimization. So the hope then is that we'll have something like this. So if this dotted dashed line, you see that's a constant performance, that is a rule-based algorithm. And then the hope is that by having data, we can actually use these machine learning techniques to generate these algorithms which can solve the problem more efficiently or in a better way, get better accuracy for some prediction problem, for example. So this is really the hope with learning algorithms, that it will behave like this teal line, that it will perform better than rule-based algorithm. But there's no guarantee that that will happen. So for a lot of problems, actually, these kind of methods are not the correct solution. I'll talk more about that later. But first of all, some examples of the kind of problems we're often looking at with machine learning. And I will highlight the kind of the kind of applications where these techniques are mature. So one of the most common ones, and one which machine learning has been used for since its inception, is really working with structured data. So machine learning is kind of an extension of statistics, could say, with some other considerations. And just like statistics often use this kind of data, machine learning does as well. So we have some kind of observations with some kind of features, and we can organize them in some kind of table. And typically there might be some of these features which we would like to understand or predict the relationship from the other features. So a classical modeling problem where we have a dependent variable and independent variables, and we want to model the relationship between them. And for these kind of problems, machine learning can at least be tried. One of the biggest challenges with these kind of problems is actually getting to this table. So you might have a problem, you might start collecting data, but how do you select what columns there should be? How do you make sure that for each observation you have a value in each of these columns? So that's often a challenge with these kind of problems. But then another important application, especially in this context, is that of anomaly detection. So we might have some kind of time series data, some observation of our process, and we would like to find a system which can detect these anomalies. This is a very useful application of machine learning. Often the challenge with using simple rule-based methods here, like a threshold, is that you will get a lot of false positives, or it's hard to balance this fact that you could also have different states of the systems, which are all normal. So imagine the time series essentially shifting between two different values. That will be difficult to use traditional methods for, depending on how regular that pattern is. So machine learning is really about trying to build methods which can detect those kind of patterns and detect deviations from them. And then another very important application where the kind of machine learning I work with, deep learning, has really changed things the last decade or so, and that is computer vision, where we now have capabilities of these machine learning systems which are much greater than 10 years ago, where we can take images and we can train these systems to detect things in these images. Like, for example, trying to segment an image based on some kind of feature we would like to detect, or finding, for example, characters or digits in an image. And then finally, one of my main areas of application is that of analyzing text, analyzing natural text. So often natural text is unstructured, so there are a lot of challenges in how do we extract the meaning of this text. This is also an area where a lot of the established techniques can actually work very well. And we've seen the last 2 or 3 years an amazing advancement in this field with the help of these deep neural network techniques. But one thing I would like to highlight, which I think is important, is that at least popularly, there's this idea of AI or machine learning as somehow we're building this intelligent agent, or we're building this autonomous agent which will be able to monitor some problem in real time, learn from it, and adapt to changes and make optimal decisions. Now, that is very rarely the case. Such control systems are typically implemented by rule-based systems. So when it comes to machine learning, autonomous agents are very rare, at least in practice. They are often more of a research or demo kind of project. There are applications where they can actually be used, and that often, if you have a high fidelity simulator, these methods can actually be quite useful. But I would say this is a very niche area of machine learning and AI in general. And there's another kind of idea that AI somehow automatically solves our problems for us. So if we want the problem of getting a suit, a tailored suit, there is, at least in some cases, this idea that AI will help us get that automatically. So it is like this robot, which just solves the problem for us. But in reality, AI and machine learning it's a set of techniques. It's a set of techniques that a skilled human uses to try to build an automatic solution to a problem. And I'd like to to make an analogy to other tools we use. So for example, in the engineering fields, using the finite element methods or partial differential equation is a very commonly used tool to model a problem. And in a similar manner, AI and machine learning are also sets of tools which we can use to try to model our problems. But what we've seen a lot, at least in the last decade or so, is this, or last 5 years perhaps, this idea that, well, we should do an AI project or we should do a machine learning project because everyone else is doing a machine learning project. But I think, just like Professor Grosche told us in the morning here, it's really important that you have a very clear understanding of your problem before you start selecting your tools. So we saw an example of how data-driven methods could be used to solve problems, but also how more classical, like finite element methods, could be used. And one important thing I also want to highlight here is that a domain expert is the person who can help you do this. So I'd like to just point out that these are modeling tools, and there's kind of on the spectrum for mechanistic or kind of more knowledge-built models, and then we have this spectrum for going to data-driven models. And here is actually something where we can make things in between here, that we can have different degrees of knowledge baked into our models. And then just more of an idea of what machine learning is and what kind of capabilities it has. So machine learning is more like machine intuition, not machine reasoning. So problems like recognizing a face is something machine learning is capable of doing, while reasoning about complex things based on world knowledge is something that machine learning does not excel at least today. There's a checklist which is useful to have to kind of understand machine learning, and that is it's defined by Erik and Tom Mitchell in this article referred here. But essentially they have 8 points, and if all of these points check out, then your problem is suitable for machine learning. So one of them is that you can define your problem as a function from well-defined inputs to well-defined outputs. Another one is that you have large amounts of data. What large means, I'll briefly mention that. And that you have a clear understanding of what the goal is and that you can measure that. Also no change of logic or reasoning, as I said before, and also no in-depth of an explanation of why a decision was made. Also that we can correlate some degree of errors. That is important. And that the phenomena should be relatively stable when it comes to the statistical properties of it. And finally, that no specialized dexterity, physical skills, or mobility is required. The last point here I think is important. It will be quite a while before we see the kind of machine learning based autonomous robots in the real world. I think we will see a lot more rule-based such before in the future. Finally, just a mention of AI. AI is a lot more than just machine learning. So there are a lot of methods we use routinely today which actually have their origin in an AI, like constraint optimization or a lot of planning methods and knowledge representations. But a final point I want to make before I wrap up talking a bit about data is that when we talk about AI in practice and putting an AI system into production, think of this as actually doing a software development project. Because there are similar challenges, like trying to understand user needs, what kind of artifact you get a software artifact, you need to deploy that like a software artifact, it fits the process it's designed for, and maintenance will have similar issues like any software system. And just as a kind of to give you an idea of what that means is that if we think of AI projects as software projects, we should probably think of the risks inherent to software projects. We see that a lot of software projects are associated with large risk. So this slide here, this is from a report which is produced on a regular basis by the Standish Group, the Chaos Report, where they try to understand how software projects actually work. We can see that for a lot of the software projects, they actually fail, almost a fifth. So we have kind of as many successful projects as failed projects, and most of them are challenged. So they go over budget, over time, or don't deliver a satisfactory result. But there is a big difference in size of projects. So for large projects, it's worse. So for really grand projects, these huge projects, it is very difficult to actually deliver a system at all. It often fails completely. While for small projects, we see the kind of the inverse. It's very rare that small projects fail. So my takeaway message here is that small is better. So aim for small projects. And then another additional challenge with machine learning problem is that of data. So in machine learning problem, getting data, managing data is always hard. So one of the key things people say is that for machine learning problems, it was more challenging than we thought working with data. And I like to get people to understand that to develop a data-driven product, a lot of the work will be need to place in the data preparation phase, a lot more than the modeling phase typically. So we as AI people or machine learning researchers, we tend to overly or perhaps emphasize the modeling phase too much, while the data phase is really in practical problems the most important part. And then a question of how much data you need, that really depends on your problem. Is the problem you're trying to model, well behaved and easy to model, then you will need less data. But if it's a complex function essentially that you're trying to approximate, you will need more data. And who knows what kind of problem you have? Well, your domain expert will know that. Then finally, just a couple of fascinating what's happening in the field. One of the really important things I think is that we're seeing these methods being used for design. Early in the design phase, we can really explore complex design spaces a lot faster using these techniques, and especially that we can have models which they suggest designs for us. And finally, there's this development of deep learning where we can work with completely new kinds of data, which I think will open up the kind of modeling toolkit a lot more. So that's it for me. And the takeaway is that machine learning is difficult. It is a challenge, and especially the data. And you need to involve your domain experts into this. So finally, I'd just like to say that what I've talked about now is part of a presentation we gave in a big project funded by the European Union for High Performance Computing. And if you're interested, please have a look here. So thank you very much.
So thank you, Erik. It was very nice to hear your inspirational talk about how to actually start with these processes and perhaps why not starting. So you said go small, that is important. But actually we work a lot in sheet metal forming with SMEs and medium-sized companies. And there could also be a problem actually to have the time to train the systems when you have decided what you want to do and you know that you can actually gain from them in the end. So do you have any advice to these companies?
So one of them is to talk with this high performance computing center, which I'm part of, where we help small companies to actually get access to high performance computing, including graphical process unit cluster or GPU clusters. So that is one way. If the training time takes too long, there are these natural resources you can apply for.
So I didn't know. Thank you very much. And also you talked about automation and design. And design for me is more geometrical and product design, but would you also consider this to be possible for complex design like production processes and production lines in the future?
Very good question. I think that's a much harder problem because I think there is so much complex details and interactions in these processes. So I think that will be difficult. I think we will need human intelligence in that problem for a long time going forwards. But I think it can help with parts of it.
And we are both in different fields of RISE. I'm domain in forming, and you are in domain in these more advanced AI things. So I think that we could collaborate more in the future. So thank you for now, and some of you will meet in the Q&A session later on. Thank you a lot.
Thank you for having me. Bye.